Hey, this is Ken Rosever, and this is class for today. Uh, 3.4, Graphing Polynomial Functions. What we're going to learn in this chapter is identifying the graph of a polynomial function, identify the graph of a polynomial function and determine its degree. We're going to be able to look at a graph and determine its degree just by looking at it, describe the end behavior of a polynomial graph. We're going to discuss attributes of a polynomial graph with zeros of multiplicity, graph polynomial functions in standard form, and solve applications. The chapter begins with this thought. If you look at the graph of f of x equals x plus 2, well, you get a graph that starts at 2 and goes up 1 over 1. How many times does it cross the x-axis? One time. It has only one root. The other equation they have here is consider the graph g of x equals x minus 1 squared. And when you look at that, let me do both of these. All right, so the first one was consider the graph of f of x equals x plus 2. And when you graph that thing, you notice that it only crosses through the x-axis one time at negative 2. Let me pause. All right, sorry about that. So when we graph this thing, it's linear. It looks like this. You all should know how to do that. And because it's like a root and there's only one, when does x plus 2 equal 0? When x equals negative 2. So it crosses at negative 2. Okay. The other one they talked about was consider g of x equals x minus 1 squared. And when you graph that, you get a parabola, and its vertex is at 1. It looks like this, and then over 1, up 1, like this. So this would be our parabola. And note with me that because the 0 has a multiplicity of 2, as we discussed in class before, that means it'll bounce off the x-axis. Anytime you have an even multiplicity, it bounces off. And where does it actually touch down? At x minus 1y, because when will y equal 0? When x equals 1. So that's our root, and it has a multiplicity of 2. Now what they show here, which is kind of interesting, when you look at this graph and its attributes, there it is. Let me minimize that. You'll notice that this graph, which is of the function, we'll call it h of x, equal to x plus 2 times x minus 1 squared, whatever that is when you multiply it out. This graph here has the attributes of both the parent functions. Okay, so this function crossed at negative 2, this function bounced off at 1, and notice the graph of this function crosses at negative 2 and bounces off at negative 1. This is an important note that um, in a graph of a function, the roots determine the crossing points and the multiplicities determine, if it's going to cross through or if it's going to bounce off or if it's going to have like a little chicane kind of deal, um, a little bend to it or sideways flattening kind of deal. So that's the first example. It's just talking about how a resulting function will share the attributes, have the attributes and behavior of the functions that you can decompose it into. Let's look at the next page. Polynomial graphs and turning points. So let me copy this. If a polynomial function of degree n if p of x is a polynomial function of degree n, then the graph has at most n minus 1 turning points. If the graph of the function P has n minus 1 turning points, and the degree of P of x must be at least n. So let's get a new page here. This is an important idea, that by looking at the number, the degree of the polynomial, we know what is the most number of places it can turn. For example, when you have a linear, the degree is 1, and therefore it has 1 minus 1 turning points, which is 0. And you see a linear graph, no matter which way you draw it, never turns, right? There's no curvature to it, there's no bend. For a quadratic, when you have x squared, that's the most basic quadratic function, you know it looks like this, and it has 1 turning point. For x cubed, now gets a little different. It's not really a turning point, but it is kind of um, a point of inflection, okay? But there's only one. Notice, it doesn't say it has to have n minus 1 turning points. It says it has to have at most n minus 1. So n minus 1 would be 3 minus 1, which is 2. So a polynomial function of degree 3 can have at most 2 turning points, okay? This one doesn't. Um, it has 1. That's okay, because its root has a degree of 3. It's 0, has a multiplicity of 3. Okay, if the graph of a function, this is the other part of this theorem, if the graph of the function p has n minus 1 turning points, then the degree of p of x is at least n. So if I show you a function that looks like this, well, that has 2, so this at least is a cubic. So this would have to have a degree that is greater than or equal to 3. If I show you this, it would have to have a degree that is greater than or equal to 2. And I'll tell you a little more about this in a second. Specifically, this one has to have a degree of 3, 5, 7. It can't be even. And this one can't be odd. So it would have to have a degree that's greater than 2, but specifically it would have to have a even degree. And this one will have to have an odd. We'll talk about that further in a little bit. So let me show you this example. Let's check our recording time. Okay, we're good. This example, example 1, asks us to determine whether each graph could be a graph of a polynomial. If not, discuss why. If so, use the number of turning points in zeros to identify the least possible degree of the function. So what I'm going to do here is I am going to copy this, but not the discussion of it. So let me go here, minimize that, new page, and we're going to paste. So here's the problem. It asks to identify whether each graph could be the graph of a polynomial. Well, first thing you need to know about all polynomial functions. Polynomial functions are smooth, continuous, and defined for all x belonging to negative infinity, all real values of x, basically. So when you look at this one, right away I can tell you this is not a polynomial function. It might be like an absolute value function because it has this very sharp point here. And what did I say over here? I said polynomial functions are smooth. So this is not a polynomial function. This one is, because it has 2 turning points, its degree must be greater than or equal to 2. Oh, my bad. 3. Let me delete that. Its degree, it's got 2 turning points, so its degree has to be at least 1 higher than that. Degree must be greater than or equal to 3. And it could be 5, it could be 7, but it can't be even. This one, it has 1, 2, 3 turning points, so its degree must be greater than or equal to 4. See how I'm adding 1 to the number of turning points. And lastly, We have this. This is discontinuous. Actually, it's not this point fills in that point, but we still call it discontinuous because it's not smooth and continuous and connected. So this is not a polynomial function. That's all for the first video.